In this section, we reverse differentiation. We begin with a rate of change and recover the family of functions that could have produced it. Differentiation moves from a quantity to its rate of change. Integration asks the reverse question. The answer is usually a family because you can't tell a function's starting point from its rate of change alone. To avoid confusion, remember that lowercase f is the function and uppercase f is one possible antiderivative for it. So if you differentiate the uppercase f, you get the lowercase f. All you need to do is differentiate each term of uppercase f. The derivative exactly matches lowercase f, so the verification is complete. Pretty easy, unless you forgot how to differentiate. The derivative of every constant is 0. Therefore, the derivative cannot tell us which vertical shift we started with. That missing information is represented by C. These functions have different heights but identical slopes at corresponding x values. The constant C represents every possible vertical shift. The integral sign asks for all antiderivatives. The dx identifies the variable, and the plus c makes the answer a family rather than a single function. The letter used for the variable does not change the integration rule. Whatever variable appears after d is the variable that appears in the antiderivative. What function has a constant rate of change k? Of course, the linear function kx. Differentiating kx gives k, which verifies the rule. The power rule reverses differentiation. Add 1 to the exponent and divide by that new exponent. Note that this rule works for any exponent n except for -1. The power rule works for positive, fractional, and negative exponents. Rewriting the integrand in exponent form often makes the correct rule immediately visible. The power rule breaks at exponent -1 because division by 0 is impossible. This is not a dead end. It is a sign that the logarithmic rule belongs here. Only a factor independent of the variable of integration may be pulled outside. Here x squared changes with x, so moving it outside would change the problem and might result in tears. Linearity allows us to integrate a polynomial or other some one term at a time. At the end, we combine all constants into one constant c. We rewrite the reciprocals as a negative powers and roots as fractional powers before integrating term by term. The derivative of the final expression returns every original term, unless you start daydreaming halfway through the calculations. The derivative of e to x is e to x. So the antiderivative of e to x is e to x. I wish all integration rules were that simple. We compensate for the factor introduced by the chain rule. Later, substitution will turn this observation into a general method. The logarithmic rule handles the one exponent excluded from the power rule. The absolute value lets the antiderivative work on intervals to either side of 0. The first and third terms use the power rule. Only 3 over x uses the logarithmic rule. Selecting the rule term by term prevents the special exponent from being overlooked. This 6-step process handles all the basic integrals in this section. Simplifying first is especially valuable because it reveals the familiar patterns hidden inside the original expression. Expanding and dividing by x squared reveals a constant, a logarithmic term, and a power term. The integration becomes routine once the algebra is finished. A differential equation gives information about a function through its derivatives. Integrating both sides recovers the general family of possible functions. The derivative determines the shape of the family. The initial condition identifies the correct vertical shift by determining c. We first integrate without using the condition. Substituting x equals 1 and f of 1 equals 10 gives c equals 6. The result satisfies both requirements. Applications follow the same initial value structure. Integrate the rate, use a known total to determine c, and check that the units change from rate units to quantity units. Velocity is the derivative of position. Integrating velocity gives the position family, and the initial position selects the correct member of that family. The membership rate gives the derivative of total membership. The current membership corresponds to time 0 and determines the constant. Once the total quantity model is known, a prediction is simply a function evaluation. Marginal revenue is the derivative of revenue. Integrating produces the revenue family, and zero sales producing zero revenue determines the constant. The rate is measured in millions of acres per year, so integrating gives millions of acres. The acreage in 2008 determines the constant. Six years after 2008 is 2014. Substituting 6 into the acreage function gives 143.4 million acres. These 6 rules form our initial integration toolkit. The power rule handles every power except -1, which belongs to the logarithmic rule. The central idea is simple. Integration reverses differentiation, but only up to a constant. When extra information is available, that constant reveals the particular function we need.